Hirap naman ito. Butiu, paturo nga. Paano ba makukuha yung...
Ano yan, mapping technique?
Oo, mapping technique sa art. Paano ba makukuha yung B, yung N, tsaka yung M dito?
Nasaan ba yung ano
ito
mo?
Yung given ko.
Yung ano ba yung B mo? Di ba yung B mo is 16, yung N mo 128. Tapos yung N mo 4K. So yung B mo ito yun. Ito yung 16 words. Tapos yung N mo, yun yung 128. Yung 128 mo ito. Tapos yung M mo, yun yung main memory. Ito nakalagay siya. Main memory consisting of 4K blocks. Tapos yun, substitute ka na lang. Solve mo na lang nun.
Hindi mo pala ka dati.
Uy, so, what's...
Uy!
Ay, nakita kami ng bibo ni Jeric doon eh.
Yan.
Ewan ko ba ng com-art? Sabong ng com-art mo?
Di ba pinag-usapan yung dyan kanina?
Com-art din. Mapping techniques. Eh, no, andyan.
Oo nga, no?
Wow.
Pati yung ano, lesson natin noon.
Pero parang weird yung book, no?
Oo nga. Lumang-luma na. Ano to?
Tingnan nyo to. Ayan.
Yan.
Uy!
Do you want to play a game? Ha 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 ha. I control this dimension. If you want to escape, you need to explain the practical introduction of computer architecture, or else you will be trapped in this world forever. Ha 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 ha.
Logo.
A proposition is a statement whose meaning terms the truth value is either true or false. A predicate is a proposition which contains one or more variables. Only when concrete values are assigned to each of the variables can the predicate be called a proposition. A connective is a statement which binds single propositions into a compound proposition. We use symbols to denote common connectives. Not X is denoted by, X and Y is denoted by X or Y, X or Y but not X and Y, X implies Y, X is equivalent to Y. A proposition or predicate involving connectives is built from terms. The connective joins together these terms into an expression. And this is the truth table. If X and Y is both false, not X is true, X and Y is false, X or Y is false, X or Y but not X and Y is false, X implies Y is true, X is equivalent to Y is true. And if X is false and Y is true, not X is equivalent to true, X and Y is false, X or Y is true, X and Y but not X or Y is true, X implies Y is true, and X is equivalent to Y is false. And if X is true and Y is false, not X is false, X and Y is false, X or Y is true, X and Y but not X or Y is false, X implies Y is false, X is equivalent to Y is false. And if X is true and Y is true, not X is false, X and Y is true, X or Y is false, X or Y but not X and Y is false, X implies Y is true, and X is equivalent to Y is true. We call two expressions logically equivalent if they are composed of the same variables and have the same truth value for every possible assignment to those variables. An expression which is equivalent to true, no matter what values are assigned to any variables, is called a tautology. An expression which is equivalent to false is called contradiction. A free variable in a given expression is one which has not yet been assigned a value. And applying a quantifier to a variable quantifies it after it has been quantified, we say it has been bound. Manipulation of expressions is governed by a number of axiomatic laws. The first one is the equivalence. When x implies y, it is equal to, and implication, x implies y is equal to, and involution, not x is equal to, and idempotency, x and x is equal to, commutativity, x and y is equal to, association, open parenthesis, x and y, close parenthesis, and z is equal to, distribution, x and open parenthesis, y or z, close parenthesis is equal to, De Morgan's, not open parenthesis, x and y, close parenthesis is equal to, identity, x and true is equal to, null, x and false is equal to, inverse x and not x is equal to,
logo.
A set is a simply well-defined collection of elements. Here, we mainly deal with sets of numbers, but it is important to note that the elements can be anything you want. Example, A is a set of 2, 3, 4, 5, 6, 7, and 8. If the element B is in the set of A, we can say that B is a member of A. The null set or empty set is a set which contains no element and is represented by the symbol, and the universal set depends on the context. Roughly speaking, it is contain every element of the problem being considered, and it is represented by the symbol of a subset, say, of A set A is such that every x member of B, we have that x member of A is denoted by. Conversely, we can say A is a superset of B and written as. Note that every set is a subset and a superset of itself, that A equals B, and if only if A is a superset of B and B superset of A is equals to B. We use the terms proper subset and proper subset, super subset, and write B, superset A, and B, proper set A, respectively. For sets A and B, we have that the union of A is, and the intersection of A and B is, the difference of A and B is, the complement of A as A is. We can say that A and B are disjoint and mutually exclusive if A intersection of B is a null set. Note also that A, the complement of operation, can be rewritten A minus B equals A intersection of B. For a given function f, we can say that f is surjective if the range equals to the codomain. There are no elements in the codomain which do not have pre-image in the domain, and injective if two elements in the domain have the same image in the range. Projective if the function is both surjective and injective. Every element in the domain is mapped to exactly one element in the codomain. The identity function f on the set A is defined I by
logo.
Boolean algebra. Most people are taught about simple numeric algebra in school. One has a set of values, say z, A list of operations, say subtraction sign, addition sign, and multiplication sign. And a list of actions which dictate how subtraction sign, addition sign, and multiplication sign work. You might not know the names for these actions, but you probably know how they work. For example, you probably know for some x, y, z, and a that x plus open parenthesis y plus z close parenthesis is equals to open parenthesis x plus y close parenthesis plus z. In the early 1840s, mathematician George Boole combined propositional logic and set theory to form a system which we now call Boolean algebra. Put simply, Boole saw that working with the logic expression x is much the same as working with the number y. One has a set of values, false and true, a list of operations, not, or, and, and a list of actions that dictate how not, or, and work. Ironically, at that time, his work was viewed as somewhat obscure, and indeed, Boole himself did not necessarily regard logic directly as a mathematical concept. However, the step of finding common themes within two such concepts and unifying them into one has been a powerful tool in mathematics, allowing more general thinking about seemingly diverse objects. It was not until 1937 that Claude Shannon, then a student of both electrical engineering and mathematics, saw the potential of using Boolean algebra to represent and manipulate digital information. A binary operation on some set A is a function, while a unary operation on A is a function. Define a set B is equals to 0 and 1, on which there are two binary operators, and or, and a unary operator not. The members of B act as identity elements for and or. These operators and identities are governed by a number of actions which should look familiar. Idempotency x or x is equals to x. Commutativity x or y is equals to y or x. Association open parenthesis x or y close parenthesis or z is equals to x or open parenthesis y or z close parenthesis. Distribution x or open parenthesis y and z close parenthesis is equals to open parenthesis x or y close parenthesis and open parenthesis x or z close parenthesis. De Morgan's not open parenthesis x or y close parenthesis is equals to not x and not y. Identity x or 0 is equals to x. Null x or 1 is equals to 1. Inverse x or negative x is equals to 1. Absorption x or open parenthesis x and y close parenthesis is equals to x. We call the and, or, and not operators as not and or respectively. Notice how this description of a Boolean algebra unifies the concepts of propositional logic and set theory. 0 and false are sort of equivalent, as are 1 and true and u. Likewise, x and y and a intersection b are sort of equivalent, as are x or y and u universal b and not x and a. You can even draw Venn diagrams to illustrate this fact. It might seem weird to see the statement x or x is equals to x written down, but we know what it means because the actions allow one to manipulate this statement as follows. X or x is equals to open parenthesis x or x close parenthesis and 1 is identity. X or x and x or not x is inverse. X or open parenthesis x and not x close parenthesis is distribution. X or 0 is inverse, while X is identity. Also notice that the and or operations in Boolean algebra behave in a similar way to multiplication sign and addition sign in a numerical algebra. For example, we have that X or 0 is equals to X, and X and 0 is equals to 0. As such, and or are often termed the product and sum operations.
Logo.
The Venn diagram, named after the mathematician John Venn, who invented the concept in 1881. The basic idea is that sets are represented by regions inside an enclosure that implicitly represents the universal set. By placing these regions inside each other and overlapping their boundaries, we can describe most set-related concepts very easily. These are the example of collection of Venn diagrams. The first one is A intersection of B. The second one is not A. The third one is A union of B. And the last one is A minus B. An n-tuple, or simply a tuple, is a sequence of n elements, open parenthesis, x sub 0, x sub 1, and so on, close parenthesis. In the specific case of n equals 2, we call x sub 0, x sub 1 a pair. And the number of elements in a particular tuple, x, may be written as absolute of x. The three binary relation. First one is the reflexive. If f, open parenthesis x and x is equals to, for all, x is a member of A. The second one is the symmetric. If f, open parenthesis x and y is equals to true, implies to f, open parenthesis y and x equals to true, for all, x, y is member of A. The third one is the transitive. If f, open parenthesis x and y is equals to true, and f, open parenthesis y is equals to z, so it equals to true. Implies f, open parenthesis x and z is equals to true, then for all x, y, and z is the z is a member of A. And the equivalence relation is the reflexive, symmetric, and the transitive that compound each other. We all know already that digital computers are the happiest when dealing binary values, 0 and 1, because they can be easily mapped onto low and high electrical signal. Let's define a Boolean algebra over the set B is equal to 0 and 1, where the meaning of the operators and or and not is described by the following table. When x is 0 and y is equal to 0, not x equals to 1. When x and y is equals to 0, x or y is equals to 0, x exclusive or y is equals to 0. While when x is equals to 0 and y is equals to 1, not x is equals to 1. X and y is equals to 0. X or y is equals to 1. X exclusive or y is equals to 1. While when x1 is x equals to 1 and y is equals to 0, not x is equals to 0. X and y is equals to 0. X or y is equals to 1. X exclusive or y is equals to 1. While in the last, when x is equals to 1 and y is equals to 1, not x is equals to 0. X and y is equals to 1. X or y is equals to 1. And not but the least, x exclusive or y is equals to 0.
Logo.
You have passed the test. You can now go back to your real world.
I'll hold the door. Please come in and just sit here for a while. This is my way of telling you I need you in my life. It's so cold without your touch. I've been dreaming way too much. Can we just turn this into reality? 'Cause I've been thinking about you lately. Maybe you could save me from this crazy world we live in. And I know we could happen, 'cause you know that I've been feeling you.